Now, when you actually train a network, right? So, one way to kind of, right, a simple way to think about it is like this, right? I mean, this is a nice example which you will find in, most probably lectures, right? If you have heard on. Okay, so it's like this, right? So suppose, so what you are trying to do is the following. Let's say, right? I mean, I've got a few points, okay, like this, okay, something like this. Okay, now this is all that I know. That means I know that, right? I mean, for some value of x, right? I mean, there is some value of y. For another value of x, this is y. This is all the data I have. Okay, and through a network, right? What you are trying to do is, so for example, right? So there is some g of x, right? Which probably, which rules these points, right? I mean, so there is a true g of x which we do not know, right? And what your network is trying to do is it is trying to figure out how to best approximate that g of x. Okay, but then the fact is g of x itself we do not know. All that we know is we have sampled g of x at certain points, right? We know that g of x takes this value at this place, right, so much, at that place so much. That's what we know. But then we don't know g of x in its entirety or anything, right? Therefore, what can happen is, right, you can, so when you have a network which is trying to get there, now it can do right, three things. One is this, okay, what is called and say underfitting. Okay, so for example, it could just probably plot a straight line. I mean, just take it as a very very naive sort of an example, right? So let's say that y hat simply does wx plus b, right? So here is x, here is your y, and you know y at some places, and this is the simplest thing, right, which you can probably do. And you know that it is not really probably, right, a good thing to do, because this is just underfitting. Now you can have, let's say, the other way, right, could be that, or maybe right on this itself I'll draw. So the other way could be that I go like that and then I fit something like that, right? And this could be, right, so this maybe I'll write this as y hat is equal to w2x square plus w1 x plus b, and so we are just looking at a scalar case. Imagine all this is happening in some high dimensional space, right, in reality. So now this is like, a second order sort of, right, a polynomial fit, and it seems to fit well. Now this would, what we will call is, let's say, appropriate fitting, okay, in a sense that, right, this we feel is probably more acceptable than the earlier one. Again, we do not know what g of x is, right, but then we feel that, right, this probably is a kind of a better way to approximate the underlying function. Then a third could be what is called overfitting, right? So an overfitting would look like this. For example, right, I do this and then I do this. Okay, that's an overfitting in the sense that, right, you have something like y hat. I hope you are able to read this. It's let's say b plus a very high, right, high degree sort of polynomial, right, I equal to 1 to 9 wi x to the power I. Okay, now you just force yourself to fit as closely as possible, right? Now the problem is, right, this is called actually overfitting. And this is a problem that you will keep on encountering. Okay, whenever you train a network, one of these things, right, will happen. And the ideal thing is to be able to get somewhere, right, where even if you make some errors with respect to the training example, that is still okay, right? Nobody is saying that you have to exactly match those values. The idea is that if I give you examples outside of it, right, you should be able to kind of, right, tell me something about what those values can be. See, for example, right, I mean, see, suppose I ask, right, what right might be the value there, okay, for y. Okay, now right, in this case, in the case of appropriate fitting, right, I have this, whereas in the case of this, whatever, right, this overfitting case, right, it looks like it's actually 0 or something, whereas in case of the line, right, I get there. Now the idea is that, see, you train a network so that it can work on examples outside what it has seen. Right? That's the whole idea. That's called a generalizability, right? You should generalize outside the set, because what is the point if I have to show, right, everything? If I have to show everything, then why do I even need a network? So the idea is that you should be able to show enough number of samples which are rich enough, right? That's where this richness comes. So if you just show some lame examples and then hope that, if you give a new example, it will try to learn something fantastic, it won't happen. So a lot depends upon what kind of examples you expose it to, and those examples should be such that they actually help this network figure out as to what probably is going on, right? And therefore, when examples come from outside of that training set, it should be able to generalize well. It should be able to predict values that are reasonable. Okay, therefore, overfitting is bad, underfitting is also bad. So what really you are looking for is that appropriate fitting, and here, even though I have shown that it goes through all the points, it doesn't have to. Okay, you don't have to meet it. You don't need a training error that is absolutely 0 or anything. You are okay with that. You can make a little amount of error. There is a small margin of error that you can tolerate, so that so that you can probably accommodate examples coming from outside the training set. You can accommodate them, accommodate in the sense that you can actually predict reasonable values for them. And there is this nice result, okay, sort of what is called an Occam's razor. Let me write that. I mean, I'm not going to talk about it much, but I like this, because what it says is, this Occam's razor. So it's a kind of a principle that says that among, let's say, competing hypotheses that explain known observations equally well, one should choose the simplest one. I mean, it's a very elegant statement, right? So it says that, right, among competing hypotheses that explain known observations equally well, choose the one, right, which is the simplest. And this also goes back to some of those relations, right, in math. If you look at the Euler relation and all, the ones that are the simplest are the ones that actually happen to be the most elegant also, right, most of the time, right. You read a paper, if somebody writes a very convoluted paper, right, and then solves a problem, at the end of the day, right, you still feel a little hollow, right, you don't really get it. Whereas, let's say this one, a Kalman filter, for example, if you read the Kalman filter, it's so nice. And then after all, I mean, the structure is simple, but then the problem that was solved was big, right. So the elegance lies in the right simplicity. Therefore, it's never a good idea to kind of put a network, with hundreds of layers, and somehow do my task and all, no, right. The idea should be to have the bare minimum that you need in order to solve a problem, right. Now here is where comes this notion of a cost surface. Okay. Now the point is, right, so you have something like a cost landscape, right. Whenever you talk about a loss, see what are you trying to do? So when you talk about a loss function, right, this is what you have at the end of the day, right. All that you have is this loss function, right. You want to be able to approximate something. It could be a regression task, it could be a classification task at the right end of the day. Now this loss function itself, right, nobody knows what kind of a landscape it has, right, because I mean, if you look at that m-dimensional, some high dimensional space, it has some kind of a landscape. And what you are trying to do is, right, you are trying to minimize this loss function with respect to, let's say, okay, now with respect to W and B, right, let me not write theta, let us say W, the weights, and then B, which is the bias, right. There could be whatever, right, millions of these weights, and then whatever, right, millions of these biases, but let us say, right, together if you call them as, let us say, theta, then theta is that kind of space, right, where you are kind of say traversing. And what you have, see, ideally, right, I mean, if you had your wish, right, you would have liked to have a cost function like that, right, but that is actually never the case. First of all, right, I mean, first thing is that because of the nonlinearities that are all sitting there, right, after all, this is the deep network with lots of nonlinearities, in the layers, right, hidden layers, and therefore definitely one doesn't expect this cost function to be as simple as that, right. You don't expect it to be a convex surface. Now, but then the interesting thing is, it is not true that, right, it is non-convex because you have a nonlinearity. It is non-convex, right, inherently. Even if I make all the activations linear, let's say, right, I don't even have the step activation at all. Everything is simply linear, right. Even then you can show that a network, right, even if you force everything to be linear, even then it does not convex. And that comes because of something called a weight symmetry, what is called a weight symmetry feature. What that really means is that, I mean, right, this I leave it to you, okay. I want you to kind of, right, think about this. So suppose I have, let's say, 1, 2, 3, okay, and then I have, let's say, 1, 2, which is my, say, this is a hidden layer. I'll just illustrate for one neuron. The same applies, I mean, if you have multiple neurons at the output. See, for example, right, so you know that right, you have these weights, right, coming from this to this to this, and similarly you have these weights, right. Now, and similarly from, let's say, here to here. Now, if you swap the neurons and the weights, right, what this means is, by which I mean, okay, let's say, let me just indicate this as 1, 2, and then 3, okay, and this is your x1, what is it, x2, x3, right. Now, if you swap the weights in the neurons, that means, right, 2 goes to 1, 1 comes to 2, right, that means you swap like this, right, and here of course it's just 3. If you had more, you would swap those also, and then if you swap the weights, okay, that means, right, I mean, what is kind of, right, going from here to here will then go from here to here. So for example, right, I mean, see, when 2 comes here, then see, this weight is what we call this as W21, right. See, when you have this x1 to 2 node connecting to 2, we call this as W21, right. Now, when 2 goes up there, then this weight is what? This is W11, right. Then that weight will then be a W21 when you swap, right. So, when you swap the weights and when you swap the neurons, and similarly, right here, this would have been W31, okay. So, instead of that, you have to swap the weights now. So, up will come W32, down will come W31. So, if you swap, right, if you swap the weights and the neuron, that means the bias will also get swapped, okay, everything will get swapped. When you swap it, right, you get the same output. Okay, which actually means that, but then if you look at in that space, right, what new set of weights you're looking at, that's not the same as what you had right originally. So if you look at each arm, right, what you had was, let's say, some weight, right, going, now that weight is changing. So it's like saying that, right, in a surface, so if you can think of this surface, right, I mean, nobody knows how that surface looks like, but then, right, you can think of it as something like that, okay, where this is the same. I mean, you have one weight configuration for which you hit the same minima, you have another weight configuration for which again you hit the same loss. You can have right, as many numbers, I mean, permutations, right, which you can do. And this is not the only symmetry that you have, there are other symmetries also. And I am saying, right, this is even if you have everything linear, you do not have to bring in non-linearities at all. Okay. So that way, a deep network, the moment you talk about a deep network, non-convexity is simply, right, inherent. Okay. There is it's not because you have non-linearities, and therefore, of course, throwing in those non-linearities, right, makes it more complex, right. But inherently it can be shown that a deep network will have there are other ways in which you can have these kind of this kind of non-convexity, right. And therefore right, what happens is but then at the end of the day, right, we don't care about it because any of these is okay for us, right. We don't care because the loss is the same. Right. So I don't have this one a preference for this weights, right, over these or over this. I don't, because as far as the loss is concerned, right, it's the same, right. And therefore, right, looking for a global minimum and all is simply out. Okay. So maybe in your other courses, right, you might have looked at nice convex functions, and then we talk about a global minimum and all, right. Nothing here. Okay. We are all happy as long as, and then the right, beauty is that there is so much so much what do you call it, so much room to go around and be able to still get things such that they are acceptable, right. That is what lends strength to these right, deep networks. Okay, I'll stop here.